Go is easy to start, but some of its bugs are surprisingly easy to miss. In this video, we will look at 15 real mistakes junior Go developers make, with broken code, the reason it fails, and the correct fix. By the end, you will recognize these bugs before they reach production. We start with Go error handling because many bugs in Go are not dramatic crashes. They are small ignored errors that let the program continue with bad assumptions. In real tools, reading configuration usually happens before the app starts. Here, we read a config file, but we throw away the error and pretend the bytes are valid. Now we run it and watch the program continue as if the file existed. Let's break down what happened. The file read failed, but because the error was ignored, the program used an empty byte slice. That makes the terminal output look normal even though startup should have stopped. Now we fix it by checking error immediately after read file. If the config cannot be loaded, we print a clear message and return before using the bytes. Now we run the fixed version and the program exits safely. The best practice here is simple. Handle the error right where the operation happens, unless your function is designed to return that error upward. This keeps the failure close to the context that explains it. This bug appears when code uses one error variable across a wider scope. Here we parse a port value, but inside the block we create a new error with, so the outer error never changes. Now we run it and the program reports success even though parsing failed. Let's unpack the result. The short declaration inside the if block introduced a new error that only exists inside that block. The later check looks at the outer error, which is still nil. Now we fix the scope by handling the parse error immediately. We store the parsed value in a clearly named variable, return on failure, and only assign port after success. Now we run it and see the real parse error. The best practice is to keep each error check close to the operation that produced it. Wide error variables make shadowing easier and make the control flow harder to trust. Next, we move to slices and output. These bugs are common because the code often compiles and loops correctly, but the data sent to users is still wrong. This matters in APIs where clients expect a list, even when there are no items. Here, our response has a nil slice, and JSON turns that into null. Now we run it and compare what the client would receive. Let's explain the output. The slice is nil, so the JSON encoder writes null. That may be technically valid JSON, but many API contracts promise an array for list fields. Now we fix the response by initializing items as an empty slice. This still means there are no users, but the JSON shape is now an array. Now we run it and the API output is clearer. The best practice is to initialize empty slices when the outside world should see an empty list. Use nil internally when it is useful, but be deliberate at API boundaries. This comes up when building a list of validation errors. In Go, append returns the updated slice, and here we discard that returned value. Now we run it and the error list is still empty. Let's look at the important detail. Append may reuse the same backing array or allocate a new one, but either way, the updated slice value comes back from append. If we throw that value away, our variable does not change. Now we fix it by assigning the result of append back to validation errors. This is the normal pattern for growing slices in Go. Now we run it and the item appears. The best practice is to always assign the append result. Usually that means assigning back to the same slice, but assigning to a new clearly named slice is also fine when you want to keep the old one. Finally, in this batch, we look at closures around loops. This is where code can look correct while every worker uses the wrong value. This shows up when launching workers for job IDs. Here, every closure reads the same variable named current, and the loop changes that variable before the workers run. Now we run it, and all workers print the final job ID. Let's break down the output. The closures do not store 101, 102, and 103 separately. They all point at current, and current ends the loop as 103. Now we fix it by creating ID inside the loop. Each closure gets its own value for that iteration, so the workers no longer share the changing variable. Now we run it, and each expected job ID appears. The best practice is to pass loop values into closures explicitly, especially when launching goroutines or storing functions for later. It makes the captured value obvious and prevents surprising worker behavior. In this section, we look at two range loop bugs that look harmless but produce surprising results in real code. Imagine we are building a filtered list of products that are in stock. I will collect pointers, then update the original products, and now we run it to see what those pointers really point to. The output still shows the old names, which is not what we wanted. Let's break down the result. In a range loop over a slice of structs, the value variable is not the element itself. It is a copy, so taking its address gives us a pointer to copy data. Now we fix it by ranging over indexes. This time the pointer is built from products at that index. So after we update the original slice, the selected pointers see the new names. The best practice here is simple. When you need pointers to slice elements, use indexes. Apply this whenever the original slice may be changed later or when you need to pass real elements around. Here we have a cart and we want to apply a 10% discount to every item. The loop looks natural, so let's run it and check the prices. The output still shows the original values. Let's explain the surprise. For a slice of structs, range gives us a copy of each item. The copy receives the discount, then disappears at the end of that loop iteration. Now we fix the loop by using the index. This line writes directly into cart at position I, and when we run it, the printed prices include the discount. The best practice is to use indexes when changing structs inside a slice. Use the value form when you only need to read data, and switch to indexes when you need to write back. Now we move to map bugs. These are small mistakes, but they can make application logic lie or crash at runtime. Let's say a login service stores failed attempts per user. Alice is not in the map, but this code reads the value directly and then we run it. The output says Alice has 0 attempts, even though there is no record for Alice at all. Let's break down the logic bug. In Go, reading a missing map key gives the 0 value for that map's value type. For int, that 0 value is perfectly believable, so the program needs one more signal. Now we fix it with the comma OK form. The value still goes into count, but OK tells us whether the key was present, and the run now reports the missing record correctly. The best practice is to use comma OK whenever 0 has real meaning in your domain. It keeps missing data from being silently treated as a valid result. Here we want to count request statuses, starting with OK. The map variable is declared so it looks ready, but now we run the code. Go panics because the map was never initialized. Let's unpack the panic. A map variable can exist and still be nil, which means it has no internal storage. Reading from it gives a 0 value, but writing needs storage, so Go stops immediately. Now we fix it by creating the map with make. The increment has real storage to write into, and when we run it, the counter prints 1 as expected. The best practice is to initialize maps before the first write. Use make for an empty map or a map literal when you already know the initial values. The final bug in this batch is about cleanup timing. It is a small ordering issue that can turn a normal file error into a panic. Here we try to open a log file and make sure it gets closed later. The problem is that we defer close before checking the open error, so let's run it with a missing file. It prints the open error, but then it also panics during deferred cleanup. Let's break down the order. OSOpen returns a nil file and a non-nil error when the file is missing, because the defer was already registered returning from main triggers file close on nil. Now we move the error check before the defer. If opening fails, we print the error and return immediately, and if it succeeds, only then do we schedule close. The best practice is to check acquisition errors first, then defer cleanup right after the success path is confirmed. This pattern works for files, network connections, response bodies, and many other resources. Now we move into resource cleanup. These bugs are easy to miss because the code may work once, but repeated calls slowly break the program. In background jobs, this shows up when we call an API many times. I will limit the client to 2 connections, then make 3 requests and intentionally leave every response body open. Now we run it and the 3rd request cannot get a free connection. Let's break down why this happens. The body is not just bytes, it is tied to the network connection. Until we close it, the transport cannot safely reuse that connection. So repeated calls can stall or exhaust resources. Now we fix the bug by closing the response body after a successful request. I also drain the body here so the connection can be reused cleanly. Now we run the fixed version and every request completes. The best habit is simple. After client, do or HTTP get succeeds, close the body. Put that cleanup right after the error check and use defer when the function is small enough for it to stay clear. Next are concurrency fundamentals. Go makes it easy to start goroutines, but shared state and program lifetimes still need explicit coordination. Imagine a small CLI that sends a notification before exiting. I will start the notification in a goroutine, but there is no coordination with main. Now we run it, and the program exits before the worker prints anything. Let's explain the result. Starting a goroutine means the work may run concurrently, not that the program will wait for it. When main returns, the whole process exits, so unfinished goroutines are stopped. Now we fix the program with a wait group. We add one worker, call done when it finishes, and wait before leaving main. Now the worker message appears before the program exits. The better pattern is to coordinate the work directly. Use a wait group when you need to wait for a set of goroutines, and use channels or context when you also need results, cancellation, or shutdown signals. This is a request counter by endpoint, a very common backend pattern. I will start two goroutines and let both increment the same map key without synchronization. Now we run it and Go catches the concurrent map right. Let's break down the crash. A map update can resize buckets and change internal pointers. If two goroutines mutate that structure at the same time, the map can become corrupted, so the runtime stops the program. Now we fix the counter with a mutex. Every increment locks the map, updates one value, and unlocks immediately. Now the final count is stable and matches the expected total. The best approach is to make ownership clear. If many goroutines share a normal map, guard it with a mutex. For specialized cases with independent keys and many reads, sync map can also be a good fit. Channels are powerful, but they are coordination tools, not magic cues. The order of sends and receives matters. Here, we want to pass a computed result through a channel. I will use an unbuffered channel and send from main before any receiver is running. Now we run it, and Go reports a deadlock. Let's unpack this. An unbuffered channel is a handoff point. The sender and receiver must meet at the same time, but main is stuck on the send, so it never reaches the receive. Now we fix the order by sending from another goroutine and receiving in main. That gives the send and receive a chance to meet. Now the value moves through the channel and prints correctly. The better way is to design channel ownership before writing the goroutines. Decide who sends, who receives, who closes the channel, and what order makes progress possible. The final bug is about production safety. Race conditions may look harmless during normal runs, but the race detector can expose the real problem. This could be a process jobs counter in a worker pool. I will increment one shared variable from two goroutines, then run the program with the race detector. The final number may even look correct, but the detector shows the unsafe access. Let's explain the warning. The expression processed ++ is a read, an addition, and a write. When two goroutines do that at once, one update can overwrite another, and the program has no reliable ordering. Now we fix the counter with atomic int64. Each worker uses add, and main reads the final value with load. Running this version with the race detector produces no warning, and the count is correct. The best production habit is to run the race detector while developing concurrent code. For shared mutable state, choose a clear protection strategy. Mutexes for group state, atomics for simple counters, or channels when ownership should move between goroutines. These Go mistakes are common, but once you understand the pattern, they become much easier to avoid. If this helps you, like the video, subscribe to Dev Level Up, and write in the comments which Go topic or bug example you want next.